Hi, class. In our discussion about the sampling distribution of the mean, we learned that the standard error is calculated as the standard deviation divided by the square root of the sample size. In statistical analysis, we almost always use sample data, not population data. Clearly, the value of the standard error is influenced by the sample size n. In addition, we usually don't know the population variance. Because of these two considerations, statisticians use the t-distribution as the sampling distribution of the mean. With large samples, say n is greater than 120, the t-distribution is virtually identical to the normal distribution. But when the sample size gets smaller, the t-distribution becomes flatter in the middle and fatter at the ends. That's why the t-distribution is used in inferential statistics when we work with sample data. It accounts for the influence of sample size. Let's look at an example to see how the t-distribution is applied in a statistical test. Suppose that we selected a sample of 64 fifth grade students from the local elementary school to take a reading test, and their average score was 72. If we know the national average score for fifth graders on this test is 75, what is the probability of getting a random sample of this size with a mean of 72 just by chance? Based on the sample data, here is what we know. The sample mean, x bar equals 72. The sample standard deviation is 12, and the sample size n is 64. The t-score, which is calculated the same way as the z-score, is t equals the difference between the sample mean and the population mean over the standard error. In our example, the standard error is 12 over the square root of 64, which is 1.5, and the t-score is 72 minus 75 over 1.5, leading to a value of -2. Based on this t-value observed from the sample, along with the degrees freedom, which is n-1, we can look it up in a t-distribution table or use an online calculator. The probability of getting the observed difference of -3, which was from 72 minus 75 by chance, if the population mean really is 75, is 0.00498. So what would you conclude? Is this sample mean significantly different from 75? Suggesting it was likely selected from a different population? Or is the difference simply due to random sampling error? This example leads us to the discussion of tests of statistical significance. Statistical significance is a measure of whether a result is likely due to chance or to a real phenomenon in the population. The process of testing for statistical significance takes the format of hypothesis testing, which follows 5 steps. Using our rating score example, we want to answer the question, is the average reading score of 5th graders in local schools significantly different from the national average? In step 1, we need to state the null and alternative hypotheses clearly. In general, the null hypothesis indicates an absence of effect. No difference between two means, no relationship between two variables, or no difference between the sample mean and the population mean. For our example, the null hypothesis is H0, mu, the population mean, equals 75. This means the sample was selected from a population with a mean of 75, and any apparent difference is due to random chance. This is always our baseline assumption and is what we typically seek to reject. The alternative hypothesis, HA, is the opposite of the null. In general, the alternative hypothesis states that there is a significant difference between means or a significant relationship between variables. Essentially, it indicates that the observed differences or relationships are not due to chance. The alternative hypothesis is also called the research hypothesis because this is usually the outcome a researcher is looking for. For our example, the alternative hypothesis HA is mu not equal to 75. Notice that the null and alternative hypotheses together cover all possible outcomes. Step 2 is when we determine the alpha value, which is the level of significance. The significance level is a threshold we set to decide whether the null hypothesis should be rejected. It's called the level of significance because if a sample statistic has a probability of occurring by chance lower than the alpha level, the result is considered statistically significant. A low probability of the observed difference happening by chance casts doubts on the null hypothesis. So the question is, how low must the probability be to reject the null hypothesis? Although there is no absolute rule, it's conventional to say that null hypothesis is most likely to be false if the probability, the p-value, is less than alpha equals 0.05. Keep in mind that we are working with the t-distribution, which is a version of the normal distribution modified for sample size. It has the same three characteristics: symmetric, asymptotic, and unimodal. Asymptotic means the two tails never touch the x-axis. So extreme values are always possible, even though their probability is very small. The alpha level is a criterion that separates extremely unlikely outcomes from those considered plausible due to random error. When alpha equals 0.05 is chosen, any outcome with a probability lower than 0.05 is considered extremely unlikely and leads to rejection of the null hypothesis. However, because the t-distribution is asymptotic, extreme values are always possible. This means we might reject a null hypothesis that is actually true. This is called a false positive or a type 1 error. So, alpha equals 0.05 means that we are willing to accept the possibility that there is a 5% chance of making a type 1 error. By setting a level of significance, we acknowledge that statistical tests never prove anything with certainty. They only provide evidence against the null. Also, be clear that alpha may vary depending on sample size, effect size, or tolerance for errors. But importantly, it should be set before data collection to avoid biasing ourselves by looking at the results first and then deciding what criterion to use. In step 3, we calculate the test statistic. In our example, we use the t-test. The observed t-value is t equals the difference between sample mean and the population mean divided by the standard error. In our case, the standard error is 12 over the square root of 64, and the t-value is -2. Yes, it's the same t-score that we previously found. The test value is what we use to assess the magnitude of the observed difference or effect. By locating this test value within the sampling distribution, we can estimate its probability of occurrence, which is called the p-value, under the assumption that the null hypothesis is true. Remember, the test value is always calculated based on the sampling distribution. Different statistics have different formulas. For example, if a z-test is used, we calculate the observed z-value. These values can be calculated by hand using distribution tables, or more commonly today, obtained through statistical software such as SPSS. Step 4 is the time to make a decision. In this step, we decide whether to reject the null hypothesis. In short, if the probability is lower than alpha, reject H0. Why? Because when a sample is drawn from a population, some difference from the population mean is expected due to random sampling error. Results that can be explained only by sampling error are not statistically meaningful. Researchers need to rule out sampling error as the cause of the observed result. This is done by comparing the test statistic with the standard error. Standard error tells us how much difference we should expect to see just by chance. If the observed test statistic is much larger than what we expect from standard error, it's unlikely to be due to chance and is called statistically significant. When alpha equals 0.05 is used, the threshold is roughly 2 standard errors away from the mean. Let's illustrate this with the sampling distribution of the mean. On the horizontal axis, all values are standard scores, showing how far a point is from the mean in units of error. In the t-distribution, similar to the normal curve, every score corresponds to a probability marked as the area under the curve. Using alpha and the degrees of freedom, we can find the critical values in the t-distribution table. Critical values mark the cutoff points that separate the rejection region from the non-rejection region. If the observed value has a p lower than alpha, it falls in the rejection region, and the null hypothesis is rejected. If p greater than alpha, it falls in the non-rejection region, and the null hypothesis is retained. Because the sampling distribution has both scores and their associated probabilities, there are two equivalent ways to make the decision. First is to compare the p-value with the alpha, which is preferred when the p is easily available. Second is to compare the observed test value with the critical value, which is common in hand calculations. Both approaches gave the same conclusion. For our example, the degrees freedom is 64 minus 1 equals 63, with alpha equals 0.05 and the observed t-value of -2. The p-value is 0.0498 from the table. Since p is lower than 0.05, we reject the null hypothesis. Step 5. Draw a conclusion. The final step is to state the conclusion in plain English with supporting evidence, but avoiding jargon. For our example, we may conclude, with alpha equals 0.05, the evidence suggests that the average reading score of fifth graders x bar equals 72 in local schools is significantly different, with p equals 0.0498 from the national average of 75. This completes a one-sample t-test, where a sample mean is compared with a given population mean. In the future, you will encounter many other statistical tests. They differ in hypotheses and test statistics, but nearly all follow these same 5 steps. That is why it is important to understand the reasoning behind them. In hypothesis testing, we also need to know the differences between directional versus non-directional hypotheses. The null hypothesis can be tested in 2 ways, as a non-directional, aka two-tailed, or a directional, aka one-tailed test. In our rating score example, the hypotheses were non-directional because they only asked if the local average was different from the national average, without predicting higher or lower. A directional hypothesis, on the other hand, specifies the direction of the difference. Using an example about how caffeine and activity level is related, the non-directional hypothesis is caffeine changes activity levels. The directional hypothesis would be caffeine increases activity levels. Another example of directional hypothesis is that H0, the mean of girls, is lower than or equals the mean of boys. And the alternative hypothesis HA is the mean of girls is greater than the mean of boys. For directional tests, there is one critical value marking the region of rejection in one tail. For non-directional tests, alpha is split into 2 tails, with 1/2 of alpha in each. Directional tests are more powerful because they concentrate probability in one tail, giving a greater chance to reach significance. But they should only be used when strong theoretical or empirical evidence justify them. Despite its popularity, hypothesis testing has 2 major drawbacks. First, it forces a yes or no decision, significant or not. But researchers often want more information, such as the strength of the effect or the range of likely values. Second, it's strongly influenced by sample size. Larger samples produce smaller standard errors, which in turn produce larger test values. This means if samples get sufficiently large, a test could almost always yield statistical significance, even when the effect is very small. To address these issues, 2 additional tools are used in inferential statistics: effect sizes and confidence intervals. Effect size measures the strength of an effect, independent of sample size. One common effect size measure is Cohen's d. Cohen's d equals the difference between the sample mean and the population mean divided by the standard deviation. This removes sample size from the calculation by using standard deviation instead of standard error. Interpretation guidelines for Cohen's d are that if d is less than 0.25, it indicates small effect. If d is between 0.25 and 0.75, it indicates moderate effects. When d is greater than 0.075, the effect size is considered strong. Different statistical tests use different effect size measures, but the purpose is always the same, to show the practical importance of a result. A confidence interval provides a range estimate of the population parameter instead of just a single value. The formula is Ci equals the mean of the sample plus or minus p with a subscript 1 minus alpha times the standard error. Continue with our rating score example. We know that the sample mean is 72 and the standard error is 1.5. With alpha equals 0.05 and the degrees freedom 63, from the t-distribution table, we can find the critical t-value is approximately 1.998. So 95% confidence interval equals 72 plus and minus 1.998 times 1.5. And the final confidence interval has a range from 69.003 to 74.997. This does not mean we are 95% sure that the population mean lies in this range. The population mean is a fixed value. Once the CI is constructed, it either contains the true mean or it doesn't. The correct interpretation is that if we repeated this sampling 100 times and calculated a 95% confidence interval each time, about 95 of those intervals would include the population mean. The confidence interval can be used to cross-validate the results of a test of significance. If the population mean falls within the range of the CI, we fail to reject the null hypothesis. Conversely, if the null hypothesis is rejected, the population mean should lie outside the range. In the rating score example, the population mean of 75 is outside the confidence interval range, and we also rejected the null hypothesis. These consistent findings provide cross-validation. A quick recap. Inferential statistics are about making inferences about a population based on data from samples. The three major tools are hypothesis testing, effect size, and confidence intervals. Hypothesis testing let us test for statistical significance. Effect size tells us how important the effect is. Confidence intervals provide an estimated range for the population parameter. Together, these tools gave researchers a fuller picture, whether results are statistically significant, how strong they are, and what range of values is most likely in the population.